Right, grade 10s, welcome again to another stunning session of physical sciences. We're going to look at the kinetic molecular theory. Alright, so the kinetic molecular theory obviously follows on from the section that we just finished where we looked at matter and classification. Okay, so now with the kinetic molecular theory, it explains the differences between the three phases of matter. Okay, now of course, we got the three phases of matter, which we have solid. Right, this is just a little recap. Liquid, as well as gas. Okay, so the kinetic molecular theory, obviously, as I just mentioned earlier, explains the differences. Okay, between the three phases that you see over here. Okay, so the kinetic molecular theory, the molecular theory states that all matter is made up of particles. All matter is made up of particles. Okay, all of it. Okay, particles, which are referred to as either molecules and or atoms. Okay, to end it off, that are in constant motion. Great. So now we're going to have a look at all these particles, or these supposed particles, in theory, because remember it's a theory that theoretically exists in all three phases of these, in all three phases of matter. Okay, so we'll start off by having a look over here at a solid. Okay, we have a solid. Okay, now according to the theory, in solids, okay, particles are very tightly bound. Right, they are tightly bound. Okay, in other words, they are compact. All right, they are tightly bound to one another. All right, and one of the thing is they can only vibrate. Okay, so if we must take a solid, for example, I'm going to draw a small solid. So this is just the face, rather, of a solid block or brick. The particles, they'd be so tightly, there'll be no space between them, almost, or very little space. Right, so we must fill up, okay, there we go. So we must fill up all these spaces here, right? They're very, very tightly compacted together. Might as well color the whole thing in, almost, right? They're very, very, very tightly kept together, okay? Very, very, almost no space for them to move freely, but they can vibrate. All right, they can only vibrate. Okay, that's the theory, or the kinetic molecular theory, within a solid, a solid object. All right, matter that's in the solid state. The next phase, of course, we'd be looking at is liquid. Write a bit of Q. Okay, in liquid. All right, now these in this state of matter, of course, particles are not like that of a solid, but rather the particles have enough, and the emphasis is on enough. Right? They have enough free space. Right? They have enough free space to move about. Okay, they have enough free space to move about, all right, and still attract one another. So they're still quite attracted to one another. Okay, so in the liquid, particles also somewhat vibrate. Okay, we take for liquid rapid boiling water. All right, there's beautiful illustrations that we were shown when I was at school, via YouTube, of course, because YouTube has everything, every single type of learning topic or subject or theory that exists is somewhat explained on YouTube. YouTube is a very good learning tool. Okay, and we were shown that when a liquid is being boiled, of course, or heated rather, the particles within water are attracted to each other for a while, and then they sort of lose interest in each other, and then they go back or move away from each other, and then they come again to each other and they move away. So they're kind of in a attract, break up, attract, break up, attract, break up, attract, break up, attract, break up. In other words, they're moving quite rapidly, attracted to each other. As the temperature increases, they obviously do that more at a faster pace or at a faster rate, right? The back and forth. Okay, so they have enough free space. So if we must look at a liquid just in a somewhat graphical representation of how it would look, okay, they're not very far apart, but at the same time they are not very close, or yeah, they're not very far, but they're not tightly compact like the solid. Okay, but they're not also very far apart either. Okay, but you can see just by doing this, there's some more space for these particles to roam or move around. Then, of course, the last phase, which is obviously a gas or gases. All right, particles are far apart. All right. In other words, they have a larger space or larger range to move. All right, they are far apart. Okay, which means they can move around freely. Move around freely. Okay, because they are far apart. Okay, so again, graphical representation, somewhat. Okay, there we go. Far apart, very far. Very far. Let's maybe make my little particles look a bit more decent, you know, for the camera. There we go. Okay, they're very far apart. Lots of range of motion for them to move. That one can go there, that one can go there, that one can go there. Bump, 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 bump. They can move right past each other, don't have to even bump into each other. Alright? They can move about freely. Let's introduce a phrase here quickly called phase change. Okay, phase change. Now, what are we referring to here? Of course, we are referring to the change of a phase, i.e. we want to change from solid to liquid, or we want to change from liquid to gas, or gas to solid, and you know, we want to change the phase. All right. So, a phase change only occurs, all right, when particles. Okay, let me dot my I's. Particles lose or they gain kinetic energy, which is energy as a result of movement or due to movement. Okay, and what would increase the kinetic energy of particles or cause also particles to lose kinetic energy? That would be temperature. For example, the temperature increases, particles have more kinetic energy. They gain if temperature increases. But if temperature decreases, they will lose kinetic energy. So if temperature changes, in other words, temperature decreases, obviously the phase change will go from a phase that has more kinetic energy or higher kinetic energy, where particles are maybe moving around freely or have more space to move around, to a phase where the particles are either tightly compact or don't have as much space. And if you heat the same object up to change it from a phase of low kinetic energy to higher kinetic energy by increasing temperature, obviously the particles will start to break free and have more space to roam around, i.e. going from a almost like a lower phase, i.e. from a solid to a liquid, or from a solid or from a liquid to a gas. That occurs, of course, in a phase change. So again, just to say it again, solids would change into liquids and liquids would change into gases. All right. When the particles gain more kinetic energy, they would vibrate quicker or more quickly, and they will move apart from one another. Okay. The kinetic molecular theory makes certain assumptions. All right. Which is obviously where all theory stems from. Okay, it stems from maybe an assumption. Okay, something that's not exactly proven true, which is a theory. Okay, like a thought. Okay, and one of the assumptions that the kinetic molecular theory assumes is that, of course, all matter is composed of small particles. Right? And then the particles of matter are in constant motion. Right? The particles of matter are in constant motion. The third assumption that it also does assume is that all collisions, okay, the particles do collide, all collisions between the particles of matter are perfectly elastic. So let's summarize maybe that part. Perfectly elastic. When we deal in grade 12 with collisions in physics, in the physicals or the physics subject of physical sciences, we try and also assume that collisions under the topic of momentum in grade 12, we assume, or we'd like to assume, that all collisions, or we'd like to prove rather that collisions are elastic, meaning the kinetic energy before equals the kinetic energy after. So the kinetic energy before the collision equals the kinetic energy after the collision. Okay, so we assume that the collision here in chemistry, under the kinetic molecular theory, where the particles are colliding with each other, that it is a perfectly elastic collision. In other words, the kinetic energy before they collided is equal to the kinetic energy when they do collide. And the fourth assumption that it assumes is particle motion. The atoms and molecules move in a straight line. Atoms and molecules move in a straight line. Okay. Between collisions. So when they collide, they move in a straight line. Okay. So I got a question about the fourth or the third assumption that the kinetic molecular theory assumes, is that all particles of matter are perfectly, or collisions rather, between particles of matter are perfectly elastic. So let's run through that explanation again. So we know that we have a formula for kinetic energy, which is EK, which is kinetic energy, the K, kinetic, E energy, is equal to half mv squared. Now, for those who are going to be watching this video, this is just for explanation purposes. Okay, so for something to be an elastic collision, all right, the EK, or the kinetic energy before, must equal the kinetic energy after the collision. So before the collision, and the particles are moving, they have a certain kinetic energy. All right, each particle has a mass. Right, an atom or molecule has a mass. All right, I'm just trying to find it here in the dot sheet. So it would have a specific mass and it would be moving at a certain velocity. Okay, so half that mass times the velocity squared of that particular particle would obviously give us a value for that particle's kinetic energy within the phase of matter. So now if it is assumed that the energy, right, which is measured in joules, all right, before the kinetic energy, because remember the particles are moving, so before it must be equal to that after for it to be considered an elastic collision. All right, an elastic collision. If you think of an elastic band, all right, if you stretch an elastic band and you let it go, it comes right back to its original form before it was stretched, right? So that's the same concept really, is that boom, before the collision happened, it had a certain kinetic energy. Both particles had a certain kinetic energy. When they collided, the kinetic energy when they collided is still the same as what it was before, i.e. doesn't change. Then we have what is called an inelastic collision. If there was kinetic energy lost, in other words, the value after here was less than that of before, in other words, it was not equal, it would have been considered inelastic. Now, grade 10s, there are in fact experiments that we can use to verify if the assumptions assumed by the kinetic molecular theory are indeed reasonable or correct, or if they are unreasonable or in fact incorrect. And one of those experiments that we can use, of course, is the Brownian motion experiment. In about 1827, long before myself and you were born, of course, Robert Brown noticed the movement of pollen grains in water, but could not explain it. Einstein realized this movement was due to the water molecules and published his first paper on the subject in 1905, 90 years before I was born. Hectic. Right, so the Brownian motion. Okay, cool. Now the Brownian motion, okay, proper definition of it is the movement of particles. Very nice one mark question. Movement of particles suspended in a fluid. Right, in a fluid, can be in a liquid or a gas. And one of those examples which we just read now about Robert Brown observing, of course, pollen grains. Okay, pollen grains in water. Okay, so I think in 1827 Robert Brown did not have access to a microscope, or even if he did, he still couldn't explain it. Okay, then Einstein came along in about the 19th century rather, and began to explain that it was due in fact to the water molecules. Okay, so if you look at pollen grains in water under a microscope, okay, we'll see that the pollen grains appear to move around on their own. Okay, but the pollen grains are actually hitting the smaller water molecules and bouncing off them. Okay, so if you look at the pollen grains under a microscope while suspended in water, you will see that they appear that they are just moving around at their own free will, you know, in water. They're just swimming, you know, they've got arms and legs and they're just swimming. Woo, yay. But no, actually that's not what's happening. They're actually bouncing off the water molecules, and that is in fact causing some movement. All right, and it appears that they are moving around on their own. Okay, but of course we know chemistry. We know that water in fact has molecules, and we are therefore able to explain that that water molecules, the molecules within the liquid phase of water, are in fact, they have the freedom and movement to move around. Okay. So we can use this Brownian motion to show that one, all matter is in fact composed of small particles. Okay, we can verify that assumption. Okay, we can also say that the particles, using this experiment, are in constant motion. All collisions between the particles of matter are perfectly elastic. Okay? The collisions are perfectly elastic. And number 4, they move in a straight line. The next experiment that we could use to prove if the 4 assumptions are in fact good assumptions or correct is known as diffusion. Now, diffusion is in fact the movement, okay, it's all movement, all got to do with movement, of particles. Okay, this one's quite a biggie. From an area of higher concentration to an area of lower concentration. And what we say with diffusion is that particles move down the concentration gradient. In other words, they come down from a higher concentration to that of a lower concentration area, of course. For example, let's take a look, all right, at a crystal. Okay, let's have a look at a crystal of potassium permanganate. Okay, potassium permanganate. Okay, the chemical formula, of course, for that is KMnO4. Okay, KMnO4, potassium permanganate. Now, when a crystal of this KMnO4, potassium permanganate, is put into a container of water, the particles of the crystal spread in the water until they are uniformly distributed. Okay? We can see this because the particles of the crystal are purple in the solution. So this would have been an experiment conducted in laboratory at school, of course, to further consolidate this section so you can see. All right. So you can obviously see this take place before your eyes, of course. I've done the experiment of crystallizing potassium permanganate, as well as done this experiment when I was at school of dropping a piece of potassium permanganate crystal into a container of water and seeing this crystal forming purple. The particles of the crystal that are forming purple in color within the solution of water, of course. Now, what does this diffusion experiment show? Okay, well, it shows that the first assumption is that indeed all matter, all right, consists of small particles. So something I didn't do for the previous experiment with the Brownian motion is just give it a tick. So it proves this one correct. And it also shows that particles, okay, in matter, or of matter, in matter, kind of trying to say the same thing, particles in matter or of matter are in constant motion. Okay, and it proves this assumption correct as well. Now the phases of matter we've obviously touched on previously at the beginning. The new term nowadays is the meninging, right? We touched on it in the meninging, or the beginning. The first one we're going to have a look at is solids. Now we all know the characteristic properties of solids is that the particles are packed closely together. Okay, it's very small spaces in between them. All right, solids in fact have fixed volume and high density, so they are very hard and they are incompressible. In other words, you cannot squish them. Right, it's not a slime ball. You can't squish them. Right, it'll keep its form no matter how hard you squeeze it in your hand. All right, you have to use a considerable amount of insane force to try and change the shape of a solid. All right, it's ridiculous. All right, ridiculous amount of strength of force. So that's some of the characteristics. But what I want to do is I would like to focus on that's solid. That's not solid. I'd like to focus on the solid, but rather the kinetic properties of it. Right? Rather have a look at the kinetic properties of a solid. Okay, so let's do that. Okay, the kinetic energy of a solid. All right, one, it is low. All right, it's very low kinetic energy. Why? Because particles are so tightly spaced or so tightly pressed together, they don't move. They only vibrate. Like if it's steel, when you heat it, they just vibrate. You know, and a vibration is usually not a big movement. It's usually a small movement. Okay, so they're very low kinetic energy. Okay. What I mentioned now, they vibrate, but they vibrate in fixed positions. Okay, so they don't move positions, they just vibrate where they are. Okay, and another thing is that the forces of attraction, all right, which does exist between these particles, by the way, forces of attraction. Okay, if you didn't know what force it was, well, it's forces of attraction, like in a magnet, of two opposite poles. Forces of attraction, of course, between these particles. Right, between these particles are strong. Right, they are strong relative to the forces of attraction between particles of the other two phases. So the forces of attraction between particles are strong relative to the forces of attraction between particles in a liquid and gas. Of the same substance. Okay, so we have a block of wood, for example. Right, we have a wooden block. All right, low kinetic energy. They are fixed. All right, they are arranged basically in a same or uniform pattern, and they are forces of attraction. So in other words, they cannot take shape of a container. If you put that same wooden block inside a big container, the wooden block will be smack bang in the middle or wherever you put it. It will not take the shape of the container. It won't fill up the shape. Okay, as we're going to see now with a liquid. All right, the liquid as well as the gas. All right, we're going to see that in just a moment. So if we have a liquid, okay, now some of the characteristics we already know, all right, that the particles of a liquid, they are packed closely together, but the spaces between them are bigger than that of solids. In other words, they have more space to, in fact, move around. And they actually can move. The particles of a liquid, they are randomly packed. There's no fixed shape within a liquid. Okay, they have a fixed volume and medium density, and they can take shape of a container. All right, they can take shape of a container. But like solids, liquid cannot be compressed. They are not compressible. Okay, the easiest way to do this is to fill a syringe. Alright, you can fill a syringe. So one experiment that we did, and I was also at school trying to understand this phases of matter. Alright, we filled a big syringe with some solid stones, and we filled the big syringe with some liquid of some sort. So we just filled it with water and changed the color. We used some water with red food coloring in it, and of course we had a gas, and we just melted the syringe end close. Right, just heated up the mouth of the syringe and just closed it so nothing could escape. And obviously couldn't compress the solid. Tried the liquid, felt like it was giving some sort of leeway, but in fact I could not compress it. And liquids, after that we found out that liquids can actually not be compressed. But having a look at the kinetic properties, which is what I want to focus on. Okay, first of all, these particles, they have more kinetic energy. Intuitively we could have that's bad. Intuitively we could have realized that, okay, that they do in fact have more kinetic energy than solid particles, or particles of a solid. Okay, the particles, they do move about freely, right? So they move about freely. Of course, they move about freely, but they are constantly attracted to each other. They are constantly attracted to each other. Right? Now, although liquids do have a fixed volume, they have an indefinite shape, and the particles are free to move about within the confines of their containers. In other words, they can, in fact, take shape of a container. Okay, so when we explain that little point there, that they can take shape of a container, that means that they are free. Although they have a fixed volume, they have an indefinite shape. In other words, their shape is not fixed, right, or predetermined, right? They are free to take whatever shape, right, they want, all right, like almost like a shapeshifter, if you want to call it that, all right, which obviously exists in like sci-fi movies and fantasy movies, of course. Shapeshifters take on any form, take on any shape, because it is indefinite. Okay. Another note worth mentioning, that the forces between particles are strong enough to keep the particles from moving away from one another completely, but they are also strong enough to prevent the particles from moving over one another randomly. So they kind of arranged in an irregular pattern, but they are attracted uniformly to each other. So they won't move over one another, they'll stay in the straight line towards each other. Okay, like I mentioned, they are because of their indefinite shape, they can take shape of a container and still move about freely, but within the confines of the container that they've taken shape to. Moving on to gases and having a look at their kinetic properties, but just to quickly go through some of their characteristic properties. Alright, so the particles of a gas, we know that they are more far apart. The spaces between them are in fact quite large. The particles of a gas, they are randomly dispersed. In other words, there's no fixed shape. Alright, no fixed shape at all. Gases, like liquids, fill the container in which they are found. So they have the volume and shape of the container. So they actually liquid, obviously, the amount of liquid that you pour into the container is the only amount of liquid that can take up the space. But a gas can take the entire liquid or the entire shape of the container. It can take it all, right? The entire shape of that container that it is found in. It has the volume and the shape of the container. And gases have low density, and in fact the third syringe in my experiment at school was in fact a gas. Because of their low density, the gases can actually be compressed. If you put some air in a syringe and you melt the mouth of the syringe close, it will you'll find that you can able to still press the syringe down, in other words, to a certain level, of course, that the gas in fact can be compressed. Okay, so they are compressible. But looking at the kinetic properties of a gas, all right, first of all, they have a lot of kinetic energy. Okay, they have a lot. In fact, they have the most kinetic energy. Okay, they have a lot of it. And the particles of gas, of course, they move about freely. Okay, which is the same words echoed in liquids. They move about freely. Okay, because of their negligible forces of attraction between the particles, so they move about freely. So they are, only difference is that they are like in liquids, they're not attracted to each other again. Okay, they have negligible force between them. So in other words, negligible, in other words, it's too small to be considered, so they're not attracted to each other again. Lots of kinetic energy, they can move faster because they are gases. Taking the gases that erupt from a volcano, we see how quickly the gas forms in the sky. The mass gas, how quickly, the sky almost disappears underneath the gases that are released from a volcano. Okay, they are free to move about, and also they are confined by a container. They take the shape of the container that they are placed in, of course. Another one that we can also maybe consider is they are independent, right? So the particles of a gas are said to be independent. They're not dependent on anything, actually. They are independent. As well as they have random motion, whereas a liquid would have a uniform motion, almost somewhat uniform motion. A solid has uniform motion, it vibrates in a fixed position, the particles. Gases actually have a random motion, all right, and they can only be confined by the container that they are found in. Okay, and another kinetic property that we could also consider, right, is that they collide with one another. Okay, so they collide, the particles, they collide with one another and move large distances between collisions. Okay, with one another and move large distances between collisions. So what do we see in the previous illustration of the liquid is that they didn't, when they collided with each other, the particles, they didn't move very far. Okay, so there wasn't a big movement or a large distance between the particles once they collided in a liquid. But in a gas, of course, the opposite is true. They move very far apart from each other when they do collide. That's why they're able to fill, fire, if wood burns, the smoke in the clouds, smoke being resembling the gas, it moves quickly. Fire can be burning down there, but you'll smell it from down here because it's moving very quickly. It's consuming a large part of the sky and traveling very fast, of course. And with that brings smell, of course. Just an example. Right, girls. Well, ladies and gentlemen, we've got a gas up top here, represented by cloud. We've got a solid over here, represented by a square-shaped object, i.e. a block. And then we got a beaker here filled with a certain liquid. Okay, so we won't call it water, we'll call it liquid rather. Alright, and we got arrows, obviously describing what is called as a phase change. Alright, so we got exhibit A, as we see in the corner there, of some type of what happens from a gas to a solid. That would be called deposition. Okay, deposition. Gas forming into a solid would be deposition. A gas that is forming into a liquid, which any geography students here would know, is condensation. Okay, we know what happens with the clouds. You know, clouds hold moisture, all right, and boom, releases water upon the earth and upon our heads and our suede shoes if we're wearing suede in the rain. Foolish idea, but it does release water. And of course, liquid to a solid, we'd obviously denote that by freezing. Okay, freezing liquid, you know, make it ice. Or in another term, crystallization. Okay, this will be our first drawing. Right, in exhibit B, we've just reversed the arrow processes now, trying to see if we go from a solid or liquid to a gas, and from a solid now to a liquid. In the previous one, exhibit A as I called it, we went from a gas to a liquid, or a gas to a solid, and then from a liquid to a solid. Now we want to see if we go from a solid to a liquid to a gas, what would it be called? Or a solid to a gas, what would it be called? So I'm just going to use another color here. So from a solid to a gas, it'll be called sublimation. Or not sublimation, sorry, excuse me, it's a sublimation rather. There's no N. Sublimation. Then from a solid to a liquid, obviously we'd melt it. Melting. Alright, if any of us have watched Shrek 2, Donkey, rain falls on him and he shouts hysterically, I'm melting, you know. I love Donkey. Anyway, I digress. A liquid, obviously a gas, we're all very well familiar with this. You don't have to be a geography student to know that when a liquid goes into a gas, we know it's called evaporation. And that explains the phase changes that happens. Okay, so we saw exhibit A, and I've seen exhibit B, where phase changes that happened in A was an example of a release of energy, where now in B, this is demonstrating the absorption of energy. Okay, this is absorption of energy, destroying. Okay, don't worry, I will come back to it. And phase A, this was of course a release. Put it back there. Release of energy. Okay, so just note those two in your drawings. And grade 10s, that is all we have time for during this tutorial. Thank you so much for joining me on our kinetic molecular theory, as well as phase changes of phases of matter. Okay, we will definitely discuss these terms in more detail in the next tutorial, so do stay tuned for more info in the next video.